This time we're going to be looking at recrystallization. So recrystallization is a common way to purify organic solids. It's often the case that our solid has slight contamination from whatever, and we need to get rid of that. So this is the technique of choice for doing so, but there's other techniques, of course, too, but this one's pretty convenient. Now, in the theory, this is the theory. So this is how this technique works. We start with a crude solid. The word crude is used to describe solids that have a little bit of contamination in them, and we need to get rid of that contamination. So it starts by placing that solid not dissolved in solvent. We just put it into a flask to start, and the size of the Erlenmeyer flask that you choose just depends on how much sample you have. We don't want to fill up the entire flask. We just want a small layer on the bottom of the flask. And in this experiment, I believe we're going to be using a 25 milliliter Erlenmeyer flask, which is the smallest. The one thing we don't want to use is a beaker, because by the time we're adding solvent and heating up that solvent, there's going to be too much evaporation of the solvent coming out of the beaker, so we don't do that. All right, so the other thing about the solvent that we're going to eventually use to recrystallize is you don't want to choose a solvent for this process that's going to immediately dissolve the solid. That's a bad thing. Otherwise, it won't work, as you'll see shortly. But we do want the solvent to dissolve the solid at high temperature. So that's how we choose the solvent. And in part B of this experiment, the second part, you're going to get a chance to choose a solvent. So you'll look at the principles involved with that. Now, for that crude solid, we haven't added any solvent to it yet. We've got a big old Erlenmeyer flask containing lots of solvent. We're heating it up. And as soon as that solvent is boiling, we add a little bit of that hot solvent to our crude solid in a different flask. And we put it on the hot plate, we start heating it up, and we're always gradually adding more and more hot solvent until the moment that the solid just dissolves. Okay, we're keeping it on the hot plate, swirling constantly. We want the solid to just dissolve in the solvent. At that point, when the last kernel of solid is dissolved, we take it off the hot plate, and the idea is to let it cool as slowly as possible. The slower you cool it, the more pure the compound's going to be. The idea is, if you do slow cooling rather than fast, birds of a feather flock together. This is the principle. So those solid molecules are going to start to crystallize very slowly, and they're going to exclude the impurities, and that's exactly how this works. So if you do this carefully enough, we don't have any of the impurities. I mean, they're still there, but they're dissolved in solution. Only our solid is there, and it's highly pure. So I'm going to diagram this in just a second so you can see this. Let's see. So finally, once we have the solid recrystallized, there's still going to be solvent present, so we have to do what's known as vacuum filtration to isolate the crystals, and all the filtrate goes through. And the filtrate contains the impurities, and we've got pure solid. So let's now describe this process using some pictures. I think that'll be a little bit easier to see what's going on. All right, so I'm going to do this. I'm going to scroll down a little bit, and I'm going to move this picture a little more to the right first. All right, so forgive my pictures as usual. I'm not very good at drawing things, but I'm going to do the best I can. Now, in a crude solid, we have it maybe initially on this little watch glass. We just did a synthesis. We've got the solid, and it's got some impurities. Right now, these little black dots that I'm doing are meant to represent the compound that we're after. This is the molecule that we just synthesized, but unfortunately, maybe what happened is we've got some slight impurities, so every once in a while we've got a molecule that's not right, and we need to remove all these little red molecules, whatever they may be. Okay, so that's the crude solid. We want to get rid of the red stuff. And like I said, the first thing we're going to do is we're going to put it into an Erlenmeyer flask, and we're not going to add any solvent initially, but all right, so let's do that. So we're going to add, that crude solid in here. So they're floating around. We've already added a bunch of hot solvent at this point, and we're right at the moment that everything, and I mean everything, is dissolved in solution. The solution's hot, and it's ready to come off the hot plate. And what happens at this point is, as we let this slowly cool, our compound is going to hopefully crystallize very nicely. In fact, the very first compound you'll see in part A has got some really, really cool crystals. They're needle-like crystals, and that's a sign that they're highly pure at that point. So if you could look at if you could look at the crystal through a very powerful microscope, you're going to see that they're very well aligned. And you've got a crystal lattice structure, and everything's hunky-dory. At the same time, the impurities, at the same time, they are excluded, so they're still dissolved in solvent, but the crystals are there, and they don't contain any more impurities at this point, so they're in the filtrate or the solvent at this point, and our crystals are solid. So now what we do is we take this flask and we cool it in an ice bath after it's cooled to room temperature. And we just want to maximize the crystallization. So if we cool it way, way down, we're going to maximize the crystals that we get back. Because if you lower the temperature of the solution, you lower the solubility of the crystals. And remember, this solid was not soluble in this solvent or room temperature to begin with. So by cooling it down, it's even less soluble. And what you do, if the crystals are really clumped up, you take your spatula and you break these up, and then you start swirling the flask, and then this whole thing gets dumped at this point. The whole flask and all the contents. Why is this not working? I can't get it to work, so we're just going to do this. So you dump the whole set of contents in here, and why does this not work? There we go. So what happens is those perfect crystalline solids are still there, and they're trapped on a piece of filter paper that's lining the bottom of this Buchner funnel, and so the solids don't come through, but at the same time, the impurities and the filtrate, all the liquid stuff, ends up down here. And so we've trapped the purified stuff. Impurities are down here. Let me just kind of indicate that. You know, all these impurities are still floating around down here. Unfortunately, a lot of the time, some of our solid is still dissolved. And so you'll see sometimes our solid crystallizing down here. And sometimes if it's a really expensive synthesis, people will try to recover those crystals. We're not going to do it this time because we'll have plenty to work with. But this is the purified solid. We take this back out. We let it air dry. Maybe we'll do some vacuum drying. But other than that, you know, this purified solid, we end up testing it. So once it comes back out of here, this is meant to represent a crystal, sorry. So this purified crystal, what we're going to do next is we're going to measure the melting point, and the melting point, depending on what it is, tells us how pure it is. And so I'll talk about how to determine the melting point eventually, but this is the general procedure. Now later in this talk, in the screencast, I'm going to show you the actual procedure. I recorded the procedures along with some help this summer, and you'll get a chance to see it for real. So let's carry on. Let's talk about the different parts in this experiment as the next thing we talk about. Okay, so in part A, we call this macro scale crystallization. This is just pretty straightforward. This is just a standard crystallization. On the cart, or on the organic cart, you're going to measure out 0.7 grams of impure sulfanilamide. You don't have to waste time being very precise with this. This is not an experiment where you have to waste gobs and gobs of time getting perfectly that. You're going to purify it by this technique we just talked about, by crystallization. Now, sulfanilamide, when you purify it, it's going to look really cool. It's got really needle-like crystals. I can't recall off the top of my head what the impurity is, but I want to say it's benzoic acid, but I'm not terribly sure. I'll have to check the text later, but there's a small amount of impurity in this. You need to get rid of it. Eventually, after you crystallize this again and purify it, you're going to measure the melting point and see how well you did on that. Now, in part B, we talked about this. So one of the important choices when you go to recrystallize something is you got to choose the appropriate solvent. So I'm going to reiterate this. The best solvent is the one that does not dissolve the organic solid at room temperature, but does dissolve the solid at high temperature. That's a key thing about choosing the solvent. And in this experiment, you're going to be issued an impure fluorine compound, not fluorine as in the F2 molecule, but fluorine as an organic compound. You're going to test it in the solvents of methyl alcohol, water, and toluene. One of these solvents is going to not dissolve at a room temperature, but it will dissolve it at a high temperature. Just follow the textbook procedure that's all described in there for doing that. Oh, by the way, once you figure out the correct solvent, then you actually do the recrystallization, you purify it. Okay, the last part, part C, there is a part D, but we're not going to do it. Part C, we're going to look at mixed melting points. And in this case, what you're going to do is you're going to select an unknown organic compound. There's going to be a bunch of little tiny vials in the cart. You just pick one of them. Keep it at your desk at all times. Don't ever put it back. I've had too many people, they grab one, they do one thing, and they put it back, and they forget which one they grabbed. So just keep it at your desk. And your job is to determine the identity of this unknown. And the general procedure for this is you're going to choose an unknown, like I said, determine the melting point for it. I'll talk about melting point determination in just a second. You're going to consult the textbook. There's a table in there that lists a bunch of compounds, and your melting point that you just figured out is going to be close to one of those two compounds. But you still can't really narrow it down to any one of those two compounds. So what you do next is you prepare two mixtures, and then you make a mixture of your compound, the one you chose, with a close compound number 1, and then your compound again with close compound number 2, according to the textbook. And then what you do is you measure the melting point for these two mixtures One of those mixtures, when you measure the melting point, is going to be the same as it was before. The other one's going to be well lower of what it should be. And the one that's the same is the correct compound, and that's the way you identify it. So you've got it. Have a nice day, and you're done with that experiment. So that's called mixed melting points. You're going to get a lot of experience measuring melting points in this class, starting with this experiment. All right, so melting point determination. This is one of the simplest ways we can assess the purity of organic solid, and that's by measuring its melting point. We'll use the Vernier melt stations. These are the newer ones. We've got about 6 of them, I think, and they're computer controlled. They're really nice compared to the melt temps. I wouldn't wish the horror of melt temps on anybody, but we may have to use them still. They're old school. Vernier is the more modern stuff, and I'll show you all that stuff in a video that's coming up next. We can always measure the melting point of a compound as a range of temperatures. This is misspelled, I apologize. So when you go to report melting point temperatures for your solid, I always want it as a range. In fact, I have to mark off people more often than not because they forget to do a range. The range starts when the compound just begins to melt, and then when it finishes melting, that's the second temperature. Always a range. It's usually at least a degree Celsius range. The more pure a compound is, the more it matches up to the literature value for that compound. So whatever your compound is that you're measuring the melting point, you'll want to look up the melting point temperature according to literature. You can do that on aldrich.com or Wikipedia, or sometimes your textbook, the Pavia textbook, has that. Impure organic solids have a lower melting point compared to literature. So if your compound's still impure, it's going to have a lower melting point and a wider range compared to literature. Okay, so those are some of the things associated with melting point determination. Like I said before, it's a very quick and easy way to assess the purity. Okay, so that's enough of the slides here. What I'm going to do next is I'm going to show you the actual procedure of both recrystallization, but also I'm going to show you the procedure for measuring the melting point. So I'm hoping you watch this because this is officially the pre-laboratory session. And of course, the nice thing about YouTube videos is you can watch these over and over again in case you forget the technique. But enjoy these videos. In this experiment, we're going to be recrystallizing impure sulfonilamide, which is a compound that's described by your textbook. These are the tools of the trade. I've got a bunch of stuff laying out here. I've got a bigger 50 milliliter Erlenmeyer flask that I've already previously put solvent into. This solvent that we're using today is, we already know what it is. It's ethyl alcohol. We're going to use that to recrystallize. The way the pump bottle works is you just simply hold the flask underneath the spigot and you just pull this up and push it down, and a little bit squirts out at a time. We only need about 20 milliliters to complete this experiment. So I'm going to go ahead and get this solvent reservoir, which we're going to use to recrystallize, on the hot plate and get that heating as soon as possible. I'm going to turn it up to about 5 to get it started, just to get it boiling in a hurry, and then I'm going to turn it back, scale it back once it gets boiling. I've also got another flask on here just in case we have to do a hot filtration. This is excessively full right now. We don't normally need it this full, but I want to make sure that it doesn't evaporate completely during the course of this experiment. We won't need to use this, but just to show you this, a hot filtration is sometimes necessary if we see that our compound is not dissolving and there's some sort of insoluble impurities inside there. And so the setup is a small flask, a little bit of solvent on the bottom. This is more than you need. A boiling stone's already in there. And actually a boiling stick would probably work better than a boiling stone, because a boiling stone is harder to get out. But last step is to fold filter paper. This is a small piece of filter paper that we're going to create what's known as fluted filter paper. And you just simply fold it in half again. Open this back up just to that point, fold it towards the center, back out, fold it towards the center again, back out. And then you take the edge and you fold backwards onto the first crease, then the second crease, then the third to the center crease. Do that on the other opposite side, back to the inner crease, forward, backwards. And then what you do is you just compress it all into an accordion shape, open it back up. And you've got what's known as fluted filter paper. The reason why we do this is it increases the surface area of the paper, and that makes the flow of the solvent through the filter paper much quicker. That just gets tucked in there. Normally, before I do a hot filtration too, I've got this already ready to go, but I take some of the hot solvent out of here and wet that entirely. If you don't have this entirely wetted, what happens is you dump your solution onto this and it starts crystallizing in the paper, and that's generally a bad thing. So you want hot solvent on here, hot solvent down here, just to prevent crystallization. But again, this is only used if you see that there's some solid impurities that just simply will not dissolve no matter what you do. It's called a hot filtration. That's what you do. In the meantime, I've got my impure sulfanilamide and I've got another flask here. I'm just going to very carefully dump this impure sulfanilamide without spilling. Entirely into the flask. I'm not going to put this onto the hot plate yet. If I tried to do that right now, I'd end up burning my solid, so I don't want to do that. The other step is, and I've already done this video once and I forgot to do this, but here I am doing it here, is to add a boiling stick, aka a popsicle stick. So you can always find these in the organic cart. You can find the boiling stones in a little cubby hole in the cart. The impure sulfanilamide is available somewhere. We've also got a pure form of sulfanilamide somewhere for later when we're starting to do melting points. But the idea here is this is impure. By recrystallization, we're hoping to purify this compound, and by the time we measure the melting point, which is our data to prove that we've purified this, we're hoping to get a good melting point out of this. All right, so right now I just got to wait for this solvent to boil, then we're going to get started on this recrystallization. Okay, I see that my solvent is just boiling in the solvent reservoir. I'm going to turn the heat back. We don't really need it at 5 at this point. I think 2 or 3 is sufficient to keep it boiling. And again, I can't stress enough, don't put your solid on the hot plate at this point. Take a clean pasture pipette, and I'm going to go ahead and wrap my little paper towel handle. These little paper towel handles, you want to make one before you start this recrystallization because this flask is going to be super hot. You don't want to be touching that with your fingers. Furthermore, just the hot vapors coming out of the top of this are enough to burn your fingers, so don't let your fingers get too high on this. I'm going to try to space my fingers back a little bit. The idea here is I'm just going to cover the solid with just enough solvent, hot solvent, to cover these crystals, and then I'm going to get in the hot plate. I want to keep it in contact with the hot plate at all times while I'm swirling. And I want to keep adding hot solvent every 10 seconds, and I don't want to slow down because if I slow down too much, the solvent is evaporating quicker than I'm adding it. So I'm going to add just enough hot solvent so that I see all the crystals are entirely dissolved. That's what I want. That's my goal. So here we go. So I'm just going to add enough hot solvent to just cover the crystals. Careful not to spill onto the hot plate too. You might get a fire if you end up spilling that ethanol on the hot plate. That's bad. Okay, that's enough to get me started. Onto the hot plate. Try not to take it off the hot plate too often. I may have to take it off just to check to see that the solid is dissolved. So every 10 seconds I'm going to want to add. Well, I'm going to wait and see that it's boiling first before I add. Okay, now it's boiling, so I'm going to put another shot in. Again, don't spill on the hot plate. You're going to end up with a fire. I'm going to check it. I know I said not to take it off the hot plate, but I just need to check it real quick. Looks like we're already there, actually. It didn't take too much hot solvent, so I'm going to take it off the hot plate. Nice thing about a boiling stick is that I can take this out easily, unlike a boiling stone, so that's why you want to use a stick. Now, I'm going to find a watch glass to put on the top of this, watch glass to put on top of the flask. Oh, it's right next to me. I didn't see it initially. And so just cover that up, prevent dust particles and other things from getting in there while it cools. You want this to cool as slowly as possible. That's why I have it on a paper towel like so. And in the meantime, I'm going to turn off the heat because I don't need this anymore. But don't throw away this solvent. We're going to use this again eventually to rinse the crystals. And I'll show you that step. That's the Buchner funnel step. But otherwise, don't throw this out. And as soon as it's cool enough for the touch, get it off the hot plate, get it cool down to room temperature, get it into ice bath as quickly as you can. All right, so we're going to wait for these crystals to crystallize. We're going to wait for this until we can touch this with our fingers. This is going to go into an ice bath. We've taken our crystals off the hot plate about 10 minutes ago. We're letting them cool down as slowly as possible. That's why I have it on a paper towel here. I've still got my watch glass. Now, once this flask is cool to the touch, I'm going to take the watch glass off and just put it in a small beaker full of ice and water. And just make sure it doesn't tip over in your beaker. That's a bad thing, of course. Meanwhile, I've got the solvent that I didn't use in the recrystallization in an ice water bath as well, because I'm going to eventually use this to rinse the crystals and also pre-wet the filter paper. But otherwise, let this sit in an ice bath for about 5 minutes before you carry on, and I'm going to show you that in just a second. Okay, we've been letting our compound sit in an ice bath for about 5 minutes now, and before I can pour it onto the Buchner funnel, I put a little piece of paper that just fits this Buchner funnel, and you can't see it right now more than likely, but there's always some filter paper available in the cart. It fits right in there. Before I can pour my stuff onto it, though, it's really important that we wet the filter paper. So take that cold solvent that we chilled down previously. I'm going to put just enough on there just to rinse the paper, get it nice and wet. And then what I'm going to do is I'm going to turn on the vacuum to hold that filter paper in place. The crystals themselves, I'm going to get those going in motion and just do a quick dump with the vacuum on. And I've got about half of them out here, so it might be necessary to add a little more solvent to your crystals. Always add the ice cold. Always add sparingly to your flask. You don't want too many of the crystals to dissolve. And if you saw that, I always get those crystals in motion before I dump. Now they're on top of the filter paper, and they're just sitting there under vacuum. I'm going to turn off the vacuum at this point. Next step is to rinse the crystals, so take more of your ice cold. And the idea here is with the vacuum off, you're just going to put enough cold solvent on top of these crystals just to rinse them. So again, sparingly. You don't want to add too much solvent to this, because more solvent means more dissolving of the crystals. Okay, again, the vacuum's off. Now I'm going to turn it back on. Rinse that solvent through. I'm going to do one more rinse. Vacuum off. Ice cold solvent. Vacuum back on. Okay, that's 2 rinses with our ice cold ethanol. Now we're just going to let this sit for about 5-10 minutes, and under vacuum those crystals are going to hopefully air dry, and we'll be ready to measure the melting point temperature of these crystals. We've been letting our crystals dry now for about 10 minutes or so in the Buchner funnel. I'm going to turn off the vacuum. One of the ironies of these crystals is they're so pure that they're going to be hard to get into this capillary tube. These are little tubes that we use for melting point determination, and ultimately we've got to get a little bit of sample in here. So I've got a mortar and pestle available here. I've got one out, and I'm going to crush up some of these needle-like crystals. They're so pure that I'm just going to crush them down just a little bit so I can get them into the capillary tube. So I'm going to scoop this up a little bit just so I get a little neat pile. Make sure that doesn't roll off the bench top. This is a capillary tube. These are always available in the rolling organic cart. There's an open end, there's a closed end. Open end, obviously, I'm going to dip just a little bit into the sample. And the golden rule is you're just going to get enough into this capillary tube that you can see it, and that's the golden rule. So if you can see it, it's enough. I'm tapping it down on the bench top just to make sure it's firmly packed into the bottom of this capillary tube. And that's pretty much the perfect amount of sample. One more little pack here. So I'm going to eventually put that into the melting point apparatus, but I need to keep track of which one's which. This is the one that I just recrystallized. I also want to run side by side with this recrystallized sample. I'm going to run impure sulfonilamide. So this is the original solid that we purified, and I want to see what the melting point difference is between impure and pure. Got too much in there this time. This one's really tough to get a small amount. That should do it. No, looks like I didn't get any in there. There we go. Again, make sure it's firmly packed into the bottom. So this one's going to be our impure. So to keep track of this, I'm going to put this mortar and pestle here. I'm going to put the impure in the middle. And now I've got a store-bought sample of sulfonilamide. I'm also going to prep this because we have it available. And this is pure sulfonilamide, just to check how I did.
Okay, I can see it, it's enough. I'm going to put this to the side. So just to recap what I've done here, I've taken my recrystallized crystals. They were rather needle-like, so I felt it necessary to crush them down a little bit in this mortar and pestle. I made a capillary here. I took some impure, the original impure sample. I made a capillary of that, middle. And then I've got some store-purchased sulfanilamide. This is highly pure. Made a sample for that so I can check my melting point. Now we're about to do a melting point. Melting point is the official method for assessing the purity of solids. It's a really important technique. We're going to be doing a lot of these this semester. So judging or obtaining the melting point for our sample, if it's right on with literature, it means our sample, we did all right, it's pure, and we'll check that now. I've got the melt station all set up and ready to go. I've loaded my capillaries into the top. Now there's a dial on the front of the melt station that, since I know what the melting point temperature is of my sulfanilamide, it's about 165 degrees Celsius. Eventually I'm going to turn this little knob to about 165 to get this whole process going. So once I turn the knob, it's going to start heating up those samples, and meanwhile I'm monitoring the data with my computer here, and I'm going to go ahead and press the start button, the collect button, and I'm going to turn this dial up. And so again, what this is going to do is it's going to heat up the samples. Now actually I'm going to go way past 165 just to get this whole ball rolling. I want the temperature to rise quickly in the beginning, and I'm going to stop heating it so rapidly right when I get to about 20 degrees. Actually with the melt stations it goes pretty quickly, pretty easily, so I'm going to stop about 10 degrees-ish, 15 degrees-ish before it gets to my melting point temperature and slow it right down. The way I'm going to slow that down is I'm going to turn it to what it should be, and that's 165 on this dial. So right now we're going to have to wait a little bit till it gets up to temperature. So again, sulfanilamide should melt at 165 to 167. That's the range literature says. My impure, on the other hand, should melt below that. We'll see what happens. I'm taking video of the samples. I'm not sure if it's going to turn out or not, but we'll take a look. Now the middle sample, keep in mind, is going to be the one that melts the earliest. That's what we predict. Okay, our impure sample is starting to melt, so we've marked the first temperature where we see the melting, and we're going to mark the second temperature once it's completely melted. Okay, now we're going to keep a close eye on our recrystallized sample. We're not going to bother with the store-bought stuff. We're just going to check to see that it melts at the same temperature, but we're only going to mark our recrystallized sample. That's the left sample. We're still watching it. We're approaching the melting point temperature. We're 3 degrees away.
Starting to melt.
Okay, our recrystallized sample just started to melt. We marked the first temperature, and now it's completely melted. So always report ranges when it comes to melting point. Notice that the store-bought melted at the exact same temperature too, so that's a good sign that our recrystallized sample was completely purified, and we're confident that we've got a good results. Once we've successfully melted our samples, we're going to turn this off, turn it into fan mode, and you'll hear a little fan kick on, and that's going to cool down the melt station so we can use it again as quickly as possible. But otherwise, we've looked at the melting point temperatures of an impure sulfanilamide sample, but also our recrystallized, and we're confident now that it melted at 165, that it's a good sample.